Somewhere in the darkness of our galaxy, a cosmic monster is breaking every rule we thought the universe obeyed. It's not a black hole, it's something even stranger, an object so powerful, so extreme, that it can tear apart atoms, warp the fabric of space, and unleash bursts of energy that outshine entire galaxies. What is this mysterious force? And could it threaten everything we know? If you're ready to journey to the edge of reality and uncover the universe's most dangerous secrets, make sure to hit that subscribe button and ring the bell. You won't want to miss what comes next, because tonight, we're about to reveal a cosmic truth that will change the way you see the night sky forever. Imagine looking up at the night sky, past the familiar constellations, past the faint glow of distant galaxies, and knowing that somewhere out there, hidden in the darkness, is an object so extreme, so violent, that it shatters the very laws of physics we thought were unbreakable. It's not a black hole. It's not the kind of cosmic villain that's been immortalized in science fiction, swallowing everything in its path. No, this is something even stranger, a cosmic monster that doesn't just bend reality, but tears it apart, atom by atom, molecule by molecule, until the very fabric of space itself is left trembling. Tonight, we're going to journey to the edge of what's possible, to a place where the rules of the universe are rewritten, and where the most powerful forces, ever unleashed, are waiting to be discovered. But before we dive into the heart of this cosmic enigma, let's set the stage. For centuries, humanity has looked to the stars and wondered what secrets they hold. We've mapped the heavens, charted the movements of planets, and even sent our machines to the farthest reaches of the solar system. We've learned that stars are born, live, and die in spectacular fashion. Some end their lives quietly, fading into white dwarfs. Others go out with a bang, exploding in supernovas that outshine entire galaxies. And then there are the black holes, those mysterious points of no return, where gravity is so strong that not even light can escape. Black holes have captured our imagination for decades. They're the ultimate destroyers, the cosmic endpoints, where matter and energy vanish from the observable universe. But what if I told you that there's something out there that's even more extreme? Something that doesn't just consume, but transforms. Something that takes the ordinary ingredients of a star and forges them into a new kind of matter, a new kind of energy, and a new kind of danger. This is the story of the Magnetar, a star that died, but refused to go quietly. A star that became a cosmic monster. Let's rewind the clock, billions of years, to the birth of a massive star. Picture a giant, burning with the energy of millions of suns, fusing hydrogen into helium, helium into carbon, and so on, building heavier and heavier elements in its core. For millions of years, this star shines, its gravity and pressure locked in a delicate balance. But eventually, the fuel runs out. The core collapses in a fraction of a second, and the outer layers rebound in a supernova explosion so bright it can be seen across the universe. Most people know this story. It's the classic tale of stellar death. But what happens next is where things get truly bizarre. If the star is massive enough, its core collapses all the way down to a black hole. But if it's just a bit less massive, say, between 8 and 20 times the mass of our Sun, something different happens. The core doesn't vanish into a singularity. Instead, it stops collapsing, held up by the quantum pressure of neutrons packed so tightly that a single teaspoon would weigh more than Mount Everest. This is a neutron star, a city-sized sphere of pure nuclear matter, spinning hundreds of times per second, with a magnetic field 1 trillion times stronger than Earth's. But even among neutron stars there are outliers. The rarest, the most extreme, are the magnetars. Born spinning even faster, with magnetic fields so intense they defy comprehension. Magnetars are the universe's ultimate laboratories for testing the limits of physics. Their magnetic fields are so strong that they can tear apart atoms, distort the vacuum of space, and unleash bursts of energy that dwarf anything else in the cosmos. In a single tenth of a second, a magnetar can release more energy than our sun will produce in 100,000 years. And yet, these monsters are only about 20 kilometers across, small enough to fit inside a city, but with a mass greater than our entire sun. So what makes a magnetar so special? It all comes down to its magnetic field. Imagine the strongest magnet you've ever seen. Maybe the kind that can lift a car or erase a hard drive from across the room. Now multiply that by a quadrillion. That's the strength of a magnetar's field. At these levels, the rules of chemistry and physics start to break down. Electrons are ripped from their orbits, atoms are stretched into bizarre shapes, and the very vacuum of space becomes a playground for quantum effects that we can barely begin to understand. But the story doesn't end there. Magnetars are not just static objects, they're dynamic, violent, and unpredictable. Their surfaces crack and quake under the strain of their own magnetic fields, unleashing flares of X-rays and gamma rays that can be detected across the galaxy. In 2004, a magnetar on the far side of the Milky Way released a burst so powerful that it affected Earth's atmosphere, even from 50,000 light-years away. If a magnetar were as close as 10 light-years, it could strip away our ozone layer and end complex life on Earth in an instant. And yet, for all their power, magnetars are elusive. We've only found about 30 confirmed magnetars in our galaxy, and there may be hundreds more lurking in the shadows, waiting for their next outburst. They're rare, they're dangerous, and they're mysterious. But they're also a window into the most extreme physics the universe has to offer, a place where gravity, magnetism, and quantum mechanics collide in ways that challenge everything we thought we knew. So tonight, we're going to peel back the layers of this cosmic mystery. We'll explore how magnetars form, what makes them so deadly, and why they might hold the key to some of the biggest questions in science. We'll compare them to black holes, neutron stars, and other cosmic phenomena, and see why, in many ways, magnetars are the true monsters of the universe. And along the way, we'll confront the limits of our own understanding, and ask what it means to live in a universe where the rules can be broken, rewritten, or simply ignored. If you could stand on the surface of a magnetar, though, of course, you couldn't, because you'd be vaporized in an instant, you'd find yourself in a world that defies every intuition you have about matter, energy, and even time itself. The gravity would be so intense that you'd weigh 200 billion times more than you do on Earth. A single step would crush you into a film just one atom thick, your molecules smeared across the iron crust like a shadow. But even if you could somehow survive the gravity, the magnetic field would be your undoing. At just a few hundred kilometers from the surface, the field is strong enough to erase every credit card, hard drive, and electronic device on the planet. Closer still, and the field begins to tear apart the very atoms in your body, stretching electrons into long, thin needles, breaking the bonds that hold molecules together. Chemistry itself ceases to function. Life, as we know it, is impossible. But the violence of a magnetar isn't limited to its immediate surroundings. These objects are restless, their surfaces constantly shifting and cracking under the strain of their own magnetic fields. when the crust of a magnetar fractures, a phenomenon known as a starquake, the energy released is almost beyond comprehension. The magnetic field lines, twisted and tangled like rubber bands stretched to their limit, snap and reconnect in a process called magnetic reconnection. This unleashes a torrent of X-rays and gamma rays blasting out into space at nearly the speed of light. In 2004, one such event sent a pulse of energy so powerful that it briefly outshone every other X-ray source in the sky, even though the magnetar was halfway across the galaxy. To put this in perspective, imagine a nuclear bomb detonating on the far side of the moon, and the flash is still bright enough to blind you on Earth. That's the kind of power we're talking about. And yet, these flares are just the tip of the iceberg. Magnetars can emit smaller bursts and pulses for weeks or months after a major quake, each one releasing more energy than our sun produces in years. The aftershocks ripple through the star's crust, sending out waves of radiation that can be detected by telescopes around the world. But what causes these starquakes in the first place? The answer lies in the unique structure of a magnetar. Unlike ordinary neutron stars, which are already among the densest objects in the universe, magnetars have an additional layer of complexity. Their crusts are made of crystalline iron, harder than diamond, floating on a sea of superfluid neutrons. The magnetic field, anchored deep within the star, twists and shifts as the magnetar spins, building up stress in the crust until something finally gives. When the crust cracks, the magnetic field lines snap and reconnect, releasing their stored energy in a violent burst. This process is not just a curiosity for astronomers. It's a window into the most extreme physics imaginable. The conditions on and around a magnetar are so far beyond anything we can create on Earth that they serve as natural laboratories for testing the limits of our theories. Quantum mechanics, general relativity, nuclear physics, all are pushed to their breaking points in the presence of a magnetar's magnetic field. For example, at distances closer than 600 kilometers from the surface, the field is so strong that it warps the vacuum of space itself, causing light to split into different polarizations, a phenomenon known as vacuum birefringence. This effect, predicted by quantum electrodynamics, has only recently been observed, thanks to the unique environment provided by magnetars. But the mysteries don't stop there. Magnetars also challenge our understanding of how stars evolve and die. Not every massive star becomes a magnetar. In fact, the conditions required are incredibly specific. The progenitor star must be massive enough to form a neutron star, but not so massive that it collapses directly into a black hole. It must also be spinning rapidly at the moment of collapse, and possess a strong magnetic field to begin with. These factors combine in a cosmic lottery, producing a magnetar only once in every 1,000 supernovae. That's why they're so rare and so valuable to science. Yet, for all their rarity, magnetars may play a crucial role in the evolution of galaxies. Their flares can inject enormous amounts of energy into the surrounding interstellar medium, triggering the formation of new stars and influencing the chemistry of entire regions of space. Some scientists even believe that magnetars are responsible for creating some of the heaviest elements in the universe, through a process known as rapid neutron capture, or the R process. When a magnetar erupts, it can blast neutron-rich material into space, where it cools and forms elements like gold, platinum, and uranium. In a very real sense, the jewelry we wear and the technology we use may owe their existence to the violent deaths of stars and the monstrous power of magnetars. But perhaps the most unsettling aspect of magnetars is their unpredictability. Unlike black holes, which are relatively stable and passive unless they're actively feeding, magnetars are ticking time bombs. They can go dormant for decades, then suddenly erupt with a flare that can be detected across the galaxy. There's no warning, no precursor, no way to predict when the next outburst will occur. For astronomers, this makes magnetars both a tantalizing target and a source of constant anxiety. For the rest of us, it's a reminder that the universe is not a safe or predictable place. It's a place of extremes, where the rules can change in an instant, and where monsters lurk in the darkness, waiting to remind us of our own fragility. If you're still picturing black holes as the ultimate cosmic threat, it's time to reconsider. Black holes are terrifying, yes, but their danger is contained. Their event horizon is a boundary. Cross it, and you're lost forever, but stay outside, and you're safe. Magnetars, on the other hand, are dangerous at a distance. Their magnetic fields reach out across thousands of kilometers, and their flares can travel for tens of thousands of light years, carrying enough energy to disrupt satellites, damage electronics, and even alter the chemistry of a planet's atmosphere. In the cosmic hierarchy of threats, magnetars are the silent assassins, rare, unpredictable, and capable of striking without warning. Let's draw a contrast. Imagine a black hole and a magnetar, both the remnants of massive stars, both only a few dozen kilometers across. The black hole sits quietly, invisible unless it's feeding on nearby matter. Its gravity is immense, but unless you stray too close, it's just another dark spot in the sky. The magnetar, by comparison, is a beacon of violence. Even when it's quiet, it emits steady pulses of X-rays and radio waves, its magnetic field warping the space around it. And when it erupts, the effects are felt across the galaxy. In 1979, a magnetar in the constellation Dorado released a burst of gamma rays so intense that it was detected by satellites orbiting Earth, even though the source was 30,000 light-years away. For a brief moment, every gamma-ray detector in the solar system was blinded by the flash. This is the kind of power that sets magnetars apart. Their flares are not just local events, they're galactic phenomena, and the consequences can be profound. If a magnetar were to flare within 10 light-years of Earth, the radiation would strip away our ozone layer, exposing the surface to deadly ultraviolet light from the sun. The result would be a mass extinction event, with consequences for every living thing on the planet. Fortunately, the odds of such an event are vanishingly small. There are no known magnetars within that range. But the fact that it's even possible is a sobering reminder of the universe's capacity for destruction. But magnetars are not just destroyers. They're also creators. Their flares and outbursts inject energy and heavy elements into the interstellar medium, seeding the birth of new stars and planets. In this way, magnetars are both the monsters and the midwives of the cosmos, shaping the evolution of galaxies in ways we're only beginning to understand. The gold in your wedding ring, the platinum in your electronics, the uranium in your reactor, all may have been forged in the heart of a magnetar, blasted into space by a flare that outshone entire galaxies. And yet, for all their power, magnetars are fleeting. Their active lifetimes are measured in thousands of years, a blink of an eye on cosmic timescales. As their magnetic fields decay, they settle down, becoming ordinary neutron stars or pulsars, their violence spent. But during their brief reign, they are the most extreme objects in the universe, pushing the boundaries of what's possible and challenging our understanding of physics at every turn. What's truly remarkable is how much we've learned about these objects in just the past few decades. For most of human history, Magnetars were unknown. Even neutron stars, their less extreme cousins, were only discovered in the 1960s. The first magnetar was identified in the late 1970s, when astronomers noticed a peculiar kind of gamma-ray burst that didn't fit any known pattern. Over time, as more data accumulated, it became clear that these bursts were coming from a new class of object, one with a magnetic field 1,000 times stronger than any other known star. The discovery of magnetars was a turning point in astrophysics. It forced scientists to rethink their models of stellar evolution, supernova explosions, and the behavior of matter under extreme conditions. It also opened up new avenues of research, from the study of quantum electrodynamics in strong fields to the search for gravitational waves from starquakes and flares. Magnetars have become a proving ground for some of the most advanced theories in physics, and a source of endless fascination for astronomers and physicists alike. But for all our progress, magnetars remain shrouded in mystery. We still don't know exactly how their magnetic fields are generated, or why some neutron stars become magnetars while others do not. We don't know what triggers their flares, or how to predict when the next outburst will occur. And we don't know what lies at the very core of these objects, whether it's a sea of neutrons, a soup of quarks, or something even stranger. What we do know is that magnetars are a reminder of the universe's capacity for surprise. They are the cosmic wild cards, the exceptions that prove the rule, the monsters that break every law we thought was unbreakable. And as we continue to study them, we're forced to confront the limits of our own knowledge, and to ask questions that have no easy answers. So the next time you look up at the night sky, remember, somewhere out there, a magnetar is waiting. It may be quiet now, its violence hidden beneath a crust of iron and neutron-rich matter. But one day, it will erupt, sending a pulse of energy across the galaxy, a reminder that in the universe, nothing is ever truly safe, and the rules are always subject to change. To truly appreciate the cosmic strangeness of magnetars, we need to zoom in on the physics that governs their existence. At the heart of every magnetar is a paradox: matter so dense it defies imagination, yet so small it could fit inside a city. The density of a magnetar is so great that a single sugar cube of its material would weigh more than all of humanity combined. This is nuclear density, where protons and neutrons are packed shoulder to shoulder, with no space between them. The forces at play here are the same ones that hold atomic nuclei together, but scaled up to astronomical proportions. But density is only part of the story. The real signature of a magnetar is its magnetic field. To understand just how extreme this is, consider that Earth's magnetic field is measured in Gauss, a unit named after the German mathematician Carl Friedrich Gauss. The strongest magnets we can create in laboratories reach about 100,000 Gauss. A typical neutron star has a magnetic field of about 1,000,000,000 Gauss. But a magnetar, its field can reach 1,000,000,000 Gauss, a number so large it's almost meaningless in everyday terms. At this strength, the magnetic field is not just a force. It's a fundamental player in the structure of matter itself. This is where the rules start to break down. In the presence of such a field, atoms are no longer spherical. The electrons are squeezed into elongated orbits, forming needle-like structures that have no analog on Earth. Chemistry as we know it ceases to function. The magnetic field is so strong that it can polarize the vacuum of space, creating pairs of particles and antiparticles out of nothing. This is quantum electrodynamics at its most extreme, a regime that can't be replicated in any laboratory, no matter how advanced. But the effects of a magnetar's field don't stop at the atomic level. They extend out into space, warping the paths of charged particles, bending light, and even affecting the structure of the star itself. The crust of a magnetar is under constant stress, twisted and deformed by the shifting magnetic field. Over time, this stress builds up until the crust cracks, releasing a burst of energy that can be detected across the galaxy. These starquakes are among the most violent events in the universe, rivaled only by supernovae and the mergers of black holes. The energy released in a single magnetar flare is staggering. In 2004, a magnetar known as SGR 180620 released a burst of energy equivalent to what our Sun produces in 150,000 years, in just a tenth of a second. The flare was so powerful that it ionized Earth's upper atmosphere, disrupting radio communications and satellite operations. And this was from a distance of 50,000 light-years. If the magnetar had been closer, the consequences would have been catastrophic. But what's even more remarkable is that we can detect these events at all. The universe is vast, and the signals from magnetars must travel across unimaginable distances before reaching our telescopes. Yet, when a magnetar flares, the burst is so intense that it can be seen from across the galaxy. This makes magnetars invaluable tools for studying the structure of the Milky Way, the distribution of matter in space, and the behavior of extreme magnetic fields. Magnetars also provide a unique window into the early universe. Some of the most distant gamma-ray bursts ever detected are thought to be caused by magnetar flares. These bursts allow astronomers to probe the conditions of the universe billions of years ago, when the first stars were forming and galaxies were taking shape. By studying the light from these events, we can learn about the composition of the early universe, the formation of heavy elements, and the processes that shaped the cosmos we see today. But for all their scientific value, magnetars remain deeply mysterious. We don't know exactly how their magnetic fields are generated or why they decay over time. We don't know what triggers their flares, or how to predict when the next one will occur. And we don't know what happens at the very core of a magnetar, whether it's a sea of neutrons, a soup of quarks, or something even stranger. What we do know is that magnetars are a reminder of the universe's capacity for surprise. They are the cosmic wildcards, the exceptions that prove the rule, the monsters that break every law we thought was unbreakable. And as we continue to study them, we're forced to confront the limits of our own knowledge, and to ask questions that have no easy answers. In the end, magnetars are both a challenge and an invitation. They challenge our understanding of physics, pushing our theories to their breaking points. But they also invite us to explore, to question, and to imagine what else might be possible in a universe where the rules are always subject to change. They remind us that the cosmos is not a finished story, but an ongoing adventure. One in which the next discovery could rewrite everything we thought we knew. If you've ever wondered how scientists even begin to study something as remote and extreme as a magnetar, the answer is as fascinating as the objects themselves. We can't visit a magnetar, and we certainly can't recreate its conditions in a laboratory. Instead, astronomers rely on the universe's own signals, bursts of X-rays, gamma rays, and radio waves that travel across the void, carrying with them the fingerprints of their violent origins. Every time a magnetar flares, it sends out a cosmic broadcast, a message written in the language of high-energy physics, waiting to be decoded by those with the right tools and the right questions. The first clues often come from space-based telescopes, orbiting high above Earth's atmosphere, where they can detect the most energetic forms of light. When a magnetar erupts, satellites like NASA's Swift, Fermi, and Chandra observatories spring into action, capturing the initial burst and tracking its afterglow. These instruments can measure the intensity, duration, and spectrum of the flare, revealing details about the energy released and the processes at work. Ground-based radio telescopes, like the Very Large Array in New Mexico or the Meerkat Array in South Africa, can pick up the faint pulses that follow, mapping the magnetar's rotation and magnetic field structure. But the real detective work happens when scientists combine data from across the electromagnetic spectrum. By comparing X-ray, gamma ray, and radio observations, they can piece together a picture of the magnetar's behavior, how its magnetic field twists and snaps, how its crust cracks and heals, and how its energy is released into space. This multi-wavelength approach is essential, because magnetars are complex, multi-layered objects. Their surfaces, interiors, and magnetospheres all interact in ways that are still not fully understood. One of the most exciting recent developments in magnetar research is the discovery of fast radio bursts, or FRBs. These are millisecond-long flashes of radio waves, some of which have been traced back to magnetars. The connection was confirmed in 2020, when a known magnetar in our galaxy produced an FRB that was detected by multiple radio telescopes. This finding has opened up a new frontier in astrophysics, linking the study of magnetars to some of the most mysterious phenomena in the universe. FRBs are now being used as cosmic probes, helping scientists map the distribution of matter in the universe and test theories of gravity and quantum mechanics. But for all the progress we've made, magnetars remain elusive. Their flares are unpredictable, their signals fleeting. Sometimes, years go by without a single outburst, and then, without warning, a magnetar will erupt, sending astronomers scrambling to capture the event. This unpredictability is both a challenge and a thrill. It means that every new observation has the potential to reveal something entirely unexpected, a new kind of flare, a new pattern of pulses, a new clue to the nature of these cosmic monsters. The study of magnetars is also a testament to the power of collaboration. No single telescope or scientist can unravel their mysteries alone. It takes a global network of observatories, sharing data and expertise, to catch these fleeting events and make sense of their signals. It takes theorists and experimentalists, working together to build models and test predictions. And it takes a willingness to embrace uncertainty, to follow the evidence wherever it leads, even when it challenges our most cherished assumptions. This spirit of discovery is what drives the field forward. Every new flare, every new burst, is a reminder that the universe is still full of surprises. Magnetars are not just objects to be studied, they are puzzles to be solved, mysteries to be unraveled, and, perhaps most importantly, invitations to wonder. They remind us that science is not just about answers, but about questions, about the thrill of the unknown, the excitement of the chase, and the joy of discovery. But the story of magnetars is not just a story of science. It's also a story of perspective. When we study these objects, we are forced to confront the scale and power of the universe and our own place within it. We are reminded that we are small, fragile creatures, living on a tiny planet in a vast and violent cosmos. And yet, we are also reminded of our capacity for understanding, our ability to reach across the void and make sense of the most extreme phenomena nature has to offer. In the end, the study of magnetars is a celebration of curiosity, a testament to the human spirit's refusal to accept the limits of knowledge. It's a journey to the edge of what's possible, a quest to understand the monsters that break every rule, and a reminder that, in the universe, the only constant is change. The deeper we venture into the world of magnetars, the more we realize how much they challenge our most fundamental ideas about the universe. For decades, black holes have been the poster children of cosmic extremity, enigmatic, all-consuming, and shrouded in mystery. But magnetars, in their own way, are even more subversive. They don't just bend the rules, they force us to rewrite them. They are the ultimate stress test for our theories, exposing the cracks in our understanding and daring us to look closer. Let's take a moment to contrast the two. Black holes are defined by their event horizons, the point of no return. Their power comes from gravity, the relentless pull that warps space and time. Magnetars, by contrast, are defined by their magnetic fields, fields so intense that they become the dominant force, overwhelming even gravity in their immediate vicinity. Where black holes are silent, swallowing light and matter without a trace, magnetars are loud, broadcasting their presence across the galaxy with bursts of radiation and pulses of energy. Black holes erase information. Magnetars create it in the form of signals that can be studied, decoded, and understood. This difference is more than academic. It shapes the way we study these objects, the questions we ask, and the tools we use. Black holes are studied indirectly, through the effects they have on their surroundings, accretion disks, jets, gravitational waves. Magnetars, on the other hand, are studied directly, through the light they emit and the signals they send. Every flare, every pulse, is a data point, a clue to the processes at work inside these cosmic engines. But the contrast goes even deeper. Black holes are, in a sense, the end of the story, the final stage of stellar evolution, the ultimate fate of matter and energy. Magnetars, by contrast, are transitional. They are born in violence, live brief but spectacular lives, and then fade away, becoming ordinary neutron stars or pulsars. Their existence is a reminder that the universe is not static, but dynamic, a place of constant change, where even the most extreme objects are only temporary. This dynamism is reflected in the way magnetars interact with their environment. Their flares can trigger the formation of new stars, enrich the interstellar medium with heavy elements, and even influence the evolution of entire galaxies. In this sense, magnetars are not just destroyers, but creators, agents of change in a universe that is always in flux. But for all their power, magnetars are also fragile. Their magnetic fields decay over time, their energy dissipates, and their violence subsides. In the end, they are transformed, their monstrous power spent, their secrets locked away in the cold, dark remnants that remain. This cycle of birth, violence, and decay is a microcosm of the universe itself, a reminder that nothing lasts forever, and that even the most extreme phenomena are part of a larger story. Yet, for all their transience, magnetars leave a lasting mark. Their flares can be detected across the galaxy. Their heavy elements can become part of new stars and planets, and their signals can teach us about the fundamental laws of nature. In this way, magnetars are both ephemeral and eternal, brief flashes of violence that echo through the cosmos, shaping the universe in ways we are only beginning to understand. As we continue to study magnetars, we are forced to confront the limits of our own knowledge. We are reminded that the universe is bigger, stranger, and more complex than we can imagine. But we are also reminded of our own capacity for discovery, our ability to ask questions, seek answers, and push the boundaries of what's possible. In the end, the story of magnetars is the story of science itself. A journey into the unknown, a quest for understanding, and a celebration of the human spirit's refusal to accept the limits of knowledge. It's a story that is still being written, with every new observation, every new discovery, and every new question that arises. To understand just how much magnetars have revolutionized our view of the cosmos, we need to look at the ripple effects their discovery has had across multiple fields of science. In astrophysics, they've forced a re-examination of how stars die and what happens in the aftermath of a supernova. In nuclear physics, they've provided a natural laboratory for matter at densities and pressures that can't be achieved on Earth. In quantum physics, they've offered a rare glimpse into the behavior of particles and fields under conditions so extreme that the vacuum itself becomes a medium, bending and splitting light in ways that defy everyday experience. Let's start with their role in stellar evolution. For a long time, the end states of massive stars seemed straightforward white dwarfs for the less massive, neutron stars for the middleweights, and black holes for the true giants. But magnetars complicate this picture. They show that not all neutron stars are created equal. The difference between a normal neutron star and a magnetar comes down to a delicate interplay of mass, rotation, and magnetic field at the moment of collapse. If the conditions are just right, the dying star's core spins rapidly enough, and its magnetic field is amplified to unimaginable strengths, creating a magnetar. This process is rare, but when it happens, it leaves behind an object that is fundamentally different from anything else in the universe. This realization has led scientists to revisit old supernova remnants, searching for the telltale signs of magnetar activity, unusual X-ray emissions, strange patterns in the surrounding gas, or the presence of heavy elements that can only be formed in the most violent stellar explosions. In some cases, what was once thought to be an ordinary neutron star has turned out to be a dormant magnetar. Its magnetic field decayed, but its history written in the scars of its environment. In nuclear physics, magnetars have become the ultimate test case for theories about the behavior of matter at extreme densities. The conditions inside a magnetar are so intense that the normal rules of atomic structure break down. Protons and neutrons are squeezed together until they form a superfluid, a state of matter that flows without friction, defying our everyday understanding of liquids and solids. Some theories suggest that, deep inside a magnetar, even the neutrons themselves may break apart, forming a soup of quarks and gluons, the building blocks of all matter. If this is true, then magnetars are not just stars, but windows into the earliest moments of the universe. When quark-gluon plasma filled the cosmos just after the Big Bang, quantum physics, too, has been transformed by the study of magnetars. Their magnetic fields are so strong that they polarize the vacuum, creating pairs of particles and antiparticles out of nothing. This phenomenon, known as vacuum birefringence, was predicted by quantum electrodynamics, but had never been observed, until astronomers turned their telescopes toward magnetars. The light from these objects is split and bent in ways that can only be explained by the presence of a polarized vacuum, providing direct evidence for one of the strangest predictions of modern physics. But perhaps the most profound impact of magnetars has been on our sense of cosmic perspective. They remind us that the universe is not a static, orderly place, but a dynamic, ever-changing arena where the rules can shift and the unexpected is always possible. They show us that even the most extreme phenomena are part of a larger story, a story of birth, death, and transformation that plays out on scales both vast and minute. Magnetars also serve as a humbling reminder of our own fragility. The same forces that create these monsters could, in theory, destroy life on Earth in an instant. Yet, they also remind us of our resilience, our ability to detect, study, and understand objects that exist far beyond our everyday experience. In doing so, they inspire us to keep exploring, keep questioning, and keep pushing the boundaries of what's possible. The story of magnetars is also a story of cosmic interconnectedness. These monsters are not isolated oddities, but key players in the grand cycles of matter and energy that shape galaxies, and ultimately, life itself. When a magnetar is born in the aftermath of a supernova, it doesn't just mark the end of a star. It sets off a chain reaction that can influence the fate of entire star systems. The energy released in a magnetar flare can compress nearby clouds of gas, triggering the birth of new stars. The heavy elements forged in its violent eruptions are scattered across space, seeding future planets with the raw materials for complex chemistry and perhaps biology. Consider, for a moment, the gold in a wedding ring or the platinum in a computer chip. These elements are too heavy to be formed in the cores of ordinary stars. Instead, they require the kind of neutron-rich environment found only in the most extreme events, supernova, neutron star mergers, and, yes, magnetar flares. When a magnetar erupts, it can hurl neutron-rich material into space at a significant fraction of the speed of light. In the milliseconds that follow rapid neutron capture, the R process builds up heavy nuclei, creating elements that will one day become part of planets, oceans, and living things. In this way, the violence of a magnetar is transformed into the building blocks of beauty and utility on Earth. But the influence of magnetars doesn't stop at the chemical level. Their flares can also shape the physical environment of their host galaxies. When a magnetar releases a giant burst of energy, it sends shockwaves rippling through the interstellar medium. These shockwaves can compress gas clouds, ignite star formation, and even clear out regions of space, creating bubbles and cavities that alter the structure of the galaxy itself. Over millions of years, the cumulative effect of many such events can reshape the distribution of stars and gas, influencing the evolution of entire galactic arms. Magnetars also play a role in some of the most mysterious phenomena in modern astronomy. Fast radio bursts, for example, are among the most enigmatic signals ever detected. These millisecond-long flashes of radio waves appear randomly across the sky, often from billions of light-years away. For years their origin was a mystery. But in 2020, astronomers traced one such burst to a known magnetar in our own galaxy, providing the first direct link between these cosmic signals and the monsters that create them. This discovery has opened up new avenues of research, as scientists now use fast radio bursts to probe the structure of the universe, map the distribution of matter, and test the limits of physics under extreme conditions. The interconnectedness of magnetars extends even to the realm of gravitational waves. When two neutron stars merge, the resulting explosion can create a magnetar, or if the mass is high enough, a black hole. The gravitational waves produced in these collisions carry information about the properties of the merging objects, including their magnetic fields. By studying these waves, scientists can learn about the birth and death of magnetars, the formation of heavy elements, and the behavior of matter at the edge of collapse. All of this points to a profound truth. Magnetars are not just cosmic curiosities, but essential actors in the drama of the universe. Their violence is not random, but purposeful, a mechanism for recycling matter, distributing energy, and driving the evolution of galaxies. They are both destroyers and creators, monsters and midwives, reminders of the universe's capacity for both chaos and order. And yet, for all their power, magnetars remain elusive. Their flares are unpredictable, their signals fleeting, and their true nature still shrouded in mystery. Each new discovery raises new questions, each answer opens up new frontiers. In this way, magnetars embody the spirit of scientific inquiry, a never-ending quest to understand the unknown, to connect the dots, and to find meaning in the chaos of the cosmos. As we continue to unravel the mysteries of magnetars, we find ourselves confronting some of the deepest questions in science and philosophy. What are the ultimate limits of matter and energy? How do the laws of physics behave when pushed to their breaking points? And what does it mean for us, fragile beings on a small planet, to exist in a universe where such monsters are possible? Magnetars force us to grapple with the concept of limits, both natural and human. In the heart of a magnetar, the density of matter approaches the theoretical maximum allowed by the laws of physics. The magnetic field strength is so high that it challenges our understanding of quantum mechanics and relativity, two pillars of modern science that usually operate in separate domains. Here they collide, and the result is a regime where new physics may emerge, where the vacuum itself becomes a medium, and where light, matter, and energy interact in ways that defy our everyday experience. This is not just an academic exercise. The study of magnetars has practical implications for our understanding of the universe. For example, the phenomenon of vacuum birefringence, where the vacuum acts like a crystal, splitting light into different polarizations, was predicted by quantum electrodynamics, but had never been observed until astronomers studied the light from magnetars. This direct observation provides a rare test of our most advanced theories, confirming predictions made decades ago and opening the door to new discoveries. But magnetars also remind us of our own limitations. Despite our technological prowess, we are still at the mercy of cosmic forces beyond our control. A single flare from a nearby magnetar could disrupt satellites, damage power grids, and even threaten life on Earth. The odds are low, but not zero, a humbling reminder that, for all our progress, we remain vulnerable to the whims of the universe. Yet, there is also a sense of empowerment in this realization. The fact that we can detect, study, and understand objects as extreme as magnetars is a testament to the power of human curiosity and ingenuity. We have built instruments that can capture the faintest whispers of radiation from across the galaxy, developed theories that can explain the behavior of matter under unimaginable conditions, and fostered a spirit of collaboration that spans continents and cultures. In doing so, we have turned the universe into our laboratory, and the monsters that once inspired fear into subjects of fascination and wonder. This journey of discovery is ongoing. Every new observation, every new flare, brings us closer to understanding the true nature of magnetars. Scientists are now searching for even more exotic phenomena, strange quark matter, color superconductivity, and other states of matter that may exist only in the hearts of these cosmic beasts. They are using gravitational waves, fast radio bursts, and high-energy neutrinos to probe the interiors of magnetars, searching for clues to the fundamental structure of reality. At the same time, magnetars are helping us explore the boundaries of life itself, by studying the effects of their radiation on planetary atmospheres. Scientists are learning about the conditions necessary for life to survive in the universe. They are asking whether planets orbiting neutron stars or magnetars could ever be habitable, and what forms of life might arise in such extreme environments. These questions are not just theoretical, they have implications for the search for extraterrestrial life, the future of space exploration, and our understanding of our own place in the cosmos. In the end, magnetars are more than just cosmic monsters. They are teachers, challengers, and guides, leading us to the edge of knowledge and daring us to look beyond. They remind us that the universe is not a finished story, but an ever-evolving tapestry of matter, energy, and possibility. And as long as we keep asking questions, keep seeking answers, and keep pushing the limits of what's possible, the story will never truly end. The allure of magnetars isn't just in their raw power or their ability to break the rules. It's in the way they force us to rethink what's possible. Every time we believe we've reached the edge of understanding, magnetars reveal a new layer of complexity, a new puzzle to solve. They are the universe's way of reminding us that certainty is an illusion, and that the cosmos is always more intricate, more surprising than we dare to imagine. Take, for example, the phenomenon of starquakes. On Earth, earthquakes are caused by the shifting of tectonic plates, releasing energy that shakes the ground. On a magnetar, the crust is a rigid lattice of iron, compressed to densities millions of times greater than steel. The magnetic field, twisted and tangled by the star's rapid rotation, exerts unimaginable stress on this crust. Eventually, the strain becomes too great, and the crust cracks, sometimes by less than a millimeter. But in that instant, the energy released is equivalent to billions of nuclear bombs detonating at once. The resulting flare can outshine entire galaxies, sending a shockwave of radiation across the universe. These starquakes are not just spectacular displays of cosmic violence. They are also windows into the interior of magnetars. By studying the timing, intensity, and spectrum of the flares, scientists can infer the properties of the crust, the structure of the magnetic field, and the dynamics of the star's rotation. In this way, each flare becomes a kind of seismograph, recording the hidden processes at work deep within the star. But the surprises don't end there. Magnetars have also been linked to some of the most enigmatic signals in astronomy, fast radio bursts, or FRBs. These millisecond-long flashes of radio waves appear seemingly at random, often from billions of light-years away. For years, their origin was a mystery, sparking wild speculation about everything from colliding black holes to alien civilizations. Then, in 2020, astronomers traced an FRB to a known magnetar in our own galaxy, providing the first concrete evidence that these monsters are capable of producing such signals. This discovery has transformed the field, opening up new avenues of research and raising new questions about the mechanisms at work. The connection between magnetars and FRBs is still being unraveled. Some scientists believe that the bursts are caused by magnetic reconnection events in the magnetar's magnetosphere, while others suggest that they may be linked to interactions with surrounding material or even with companion stars. Whatever the cause, the fact that magnetars can produce such powerful, coherent radio signals is a testament to the complexity and versatility of these objects. Magnetars also challenge our understanding of the life cycles of stars. Traditionally, the end of a massive star's life was seen as a straightforward process, a supernova explosion, followed by the formation of a neutron star or black hole. But magnetars show that the story is far more nuanced. The conditions required to create a magnetar, a rapidly spinning core, a strong seed magnetic field, and just the right mass, are rare. But when they occur, they produce an object that is fundamentally different from anything else in the universe. This realization has led scientists to revisit old supernova remnants, searching for evidence of past magnetar activity, and rethinking the pathways by which stars live and die. In all these ways, magnetars serve as cosmic laboratories, testing the limits of physics and expanding the boundaries of knowledge. They remind us that the universe is not a static, predictable place, but a dynamic, ever-changing arena where the rules are always up for negotiation. And they invite us to keep exploring, keep questioning, and keep pushing the limits of what's possible. As we approach the final stretch of our journey into the world of magnetars, it's worth reflecting on how these cosmic monsters have changed not just our science, but our sense of wonder. For centuries, humanity has looked to the stars for meaning, for inspiration, and for a sense of our place in the universe. Magnetars, with their unimaginable power and their ability to break the rules, have become symbols of both the universe's danger and its beauty. A reminder that the cosmos is as much a realm of awe as it is of fear. The philosophical implications of magnetars are profound. They force us to confront the reality that the universe is not built for us, nor is it obliged to be gentle. The same forces that create the conditions for life, stellar birth, the forging of elements, the gentle warmth of a stable sun, are also capable of unleashing destruction on a scale that dwarfs anything we can imagine. Magnetars are a stark illustration of this duality. They are both creators and destroyers, midwives and monsters, reminders that the universe is a place of balance between chaos and order. Yet, in the face of such cosmic violence, we find meaning. The very fact that we can study magnetars, that we can detect their flares from across the galaxy and decode their signals, is a testament to the resilience and ingenuity of the human mind. We have built instruments that can capture the faintest whispers of radiation, developed theories that can explain the behavior of matter under unimaginable conditions, and fostered a spirit of collaboration that spans continents and cultures. In doing so, we have turned the universe into our laboratory, and the monsters that once inspired fear into subjects of fascination and wonder. This sense of wonder is not just an abstract feeling, it has practical consequences. The study of magnetars has driven advances in technology, from the development of more sensitive detectors to the creation of new data analysis techniques. It has inspired new generations of scientists, engineers, and explorers, all eager to push the boundaries of what's possible. And it has fostered a sense of global community, as researchers from around the world work together to unravel the mysteries of the cosmos. But perhaps the most important lesson of magnetars is the reminder that knowledge is always provisional. Every time we think we have the universe figured out, a new discovery forces us to revise our theories, rethink our assumptions, and embrace the unknown. Magnetars are the ultimate wild cards, objects that break every rule, defy every expectation, and keep us humble in the face of the infinite. This humility is not a weakness, but a strength. It is the engine of progress, the spark that drives us to keep asking questions, keep seeking answers, and keep exploring the unknown. It is what allows us to turn fear into curiosity, danger into discovery, and chaos into understanding. In this way, magnetars are not just cosmic monsters, but cosmic teachers, guides that lead us to the edge of knowledge and dare us to look beyond. As we continue to study magnetars, we are reminded that the universe is not a finished story, but an ever-evolving tapestry of matter, energy, and possibility. Each new observation, each new flare, is a new chapter in that story, a chapter that we are privileged to read, and, in some small way, to write. So, as we close our exploration of the cosmic monster that breaks every rule, and isn't a black hole, We find ourselves standing at the intersection of knowledge and mystery, awe and humility. Magnetars, in all their terrifying glory, are more than just astronomical curiosities. They are the universe's way of showing us that the cosmos is not only stranger than we imagine, but stranger than we can imagine. They are the ultimate stress test for our theories, the wild cards that force us to keep our minds open and our questions sharp. Let's return for a moment to the beginning, the night sky, vast and silent, filled with the light of stars both living and dead. Somewhere out there, a magnetar spins, its magnetic field twisting space, its crust straining under forces that defy comprehension. It may be quiet now, but at any moment, it could erupt, sending a pulse of energy across the galaxy, a reminder that the universe is alive with forces beyond our control. And yet, it is precisely this unpredictability, this capacity for surprise, that makes the cosmos so endlessly fascinating. Magnetars are a testament to the power of extremes. They show us what happens when the ordinary rules are pushed to their limits, when gravity, magnetism, and quantum mechanics collide in a cosmic dance that produces something wholly new. They remind us that the universe is not a static, predictable machine, but a living, evolving system, full of surprises and possibilities. In their brief, violent lives, magnetars shape the evolution of galaxies, forge the elements that make up our world, and send signals that travel across the vastness of space and time. But perhaps the greatest lesson of magnetars is what they reveal about us. For all our vulnerability, for all our smallness in the face of cosmic forces, we are capable of understanding. We are able to build instruments that can detect the faintest echoes of a magnetar's flare, to develop theories that explain the behavior of matter under the most extreme conditions, and to collaborate across borders and disciplines in pursuit of knowledge. In studying magnetars, we are not just learning about the universe. We are learning about ourselves, about the power of curiosity, the resilience of the human spirit, and the endless capacity for wonder. This journey is far from over. Every new discovery about magnetars opens up new questions, new frontiers to explore. Scientists are now searching for even more exotic states of matter in the hearts of these stars, using gravitational waves and fast radio bursts to probe their interiors, and developing new models to explain their unpredictable behavior. The next decade promises to be a golden age of discovery, as new telescopes and detectors come online, and as our understanding of the universe deepens. And yet, for all we have learned, the most important truth may be the simplest. The universe is a place of balance. Creation and destruction, order and chaos, beauty and terror, all coexist, all are necessary. Magnetars embody this balance. They are both monsters and midwives, destroyers and creators, reminders that the same forces that threaten life also make it possible. Without the violence of magnetars, there would be no gold in our rings, no platinum in our electronics, no heavy elements in our bodies. We are, in a very real sense, the children of cosmic monsters. So the next time you look up at the night sky, remember, somewhere out there, a magnetar is waiting. It may be silent for now, its violence hidden beneath a crust of iron and neutron-rich matter. But one day, it will erupt, sending a message across the galaxy, a message that we, with all our ingenuity and curiosity, are able to receive and understand. In that moment we are connected, not just to the stars, but to the story of the universe itself. This is the legacy of magnetars. They are not just objects to be feared or studied, but reminders of the universe's infinite capacity for surprise. They teach us that the rules are never final, that knowledge is always provisional, and that the greatest discoveries are yet to come. They invite us to keep exploring, keep questioning, and keep dreaming, because in the end, the universe is not just a place we inhabit, but a story we are privileged to help write. Thank you for joining me on this journey to the edge of what's possible. The cosmic monster that breaks every rule is out there, waiting to be discovered, waiting to teach us something new. And as long as we keep looking up, keep asking questions, and keep embracing the unknown, we will never run out of mysteries to explore.